We're going to keep on and we're going to look at dilations. And dilations is going to be the first time that we're not going to have an isometry, because a dilation is about changing the size of the image. A different type of transformation is created when we project something on a screen. So think about the old slide projectors. When you actually project that onto the screen, it's much bigger. That's a dilation. It's increasing or decreasing the size of something, and by definition, therefore, it's not an isometry. Most of these projectors have a scale factor of 20. That's kind of the rule of thumb when we're actually projecting things. So I have my original image and my blown up enlarged image. In the coordinate plane, we can actually find the distance and the scale factor to figure out if I have a enlargement or if I have a reduction. The key thing here is going to make sure that your students understand that A is my starting image, the black triangle. The blue triangle is my finishing image. So if I'm looking at this, it's an enlargement, not a reduction. So my scale factor had better be bigger than 1. That's something that we run into a lot. If I'm looking at a dilation, I'm going to signify the points with the prime letters just like I did there. I basically am using a scale factor to multiply every coordinate or every length of a shape by the same value. So when I'm doing that, we're using a scale factor to be able to make sure that all the distances are increased by the same amount. So if I'm looking at this image here of this quadrilateral under a dilation centered at 0, and I want a scale factor 2/3, this is kind of a sketch of what that would look like. In the coordinate plane, it's going to be easier because I'm just going to take 2/3 and I'm going to work that through every corner, the coordinates at the corner. So if I have a dilation, I have to make sure that A, it's got to be greater than 0. I can't have a negative scale factor. It has to be positive. The image has to align and have the same scale factor for every side of the image. And all of the angles have to be congruent to the original image. So if I'm looking to know if ABC is going to be a dilation, or ACB is a dilation of AED, I'm going to take the ratio of the sides. So I know that AB is going to be 4 units, and then AD is going to be 2 units, so I get 2. Then I'm going to go ahead and compare AE to AC, and I get another scale factor of 2. So that's telling me that I'm utilizing the same scale factor, and I'm doubling the original size of that triangle. If I want to show here that something is an image under a succession of isometries, which means more than one, first I have to figure out, well, I want to do a half turn or a rotation to get the triangle upright. Once I have the triangle upright, then I can figure out, okay, is this a dilation? Now notice the prime is at Q and P, so this is actually something has happened to this larger triangle to make it smaller and be rotated. So when I'm looking at the scale factor, I have to account for what's happening there because this is my original image. So I'm looking like I'm halving this because I'm getting a scale factor of 2, but it is a reduction, which would be 1/2. So triangle AQP would be 1/2 of triangle ACB here. Two figures are going to be similar, and this is how we're going to define similarity, if I can transform one into the other utilizing isometries or a sequence of isometries, then followed by a dilation. So similar figures have to have that dilation happening with them. One application of this, so how are we going to use this in our classroom, is perspective drawing. So this is actually really neat when you teach it as an application of art within your classroom. So it's a great way to do that, to be able to get a nice image and to show them what a scale factor actually does and how it looks in real life. So every time we look in our side view mirror, we are seeing a scale down because it has that nice warning on it. That's another great way to connect this idea for your students, because it's all about connecting them to the actual applications of what these transformations are used in.